Hi thinkers, welcome to the Data Structures in Python course on thinkexacademy.com. In this tutorial, we are going to study about binary trees and we are going to cover all the important points related to the binary trees topic. So far, we have already studied data structures like linked list, queues, and stacks. All of these data structures are basically linear data structures, which means that the data will be stored in a linear fashion in those data structure, which basically is a constraint as it gives us the time complexity of big O of n, which is in the case of linked list and stacks and queues, etc. Now, in order to make this time complexity much better, in order to reduce the time complexity, binary tree data structures are really helpful because they form a different type of a structure, which is a non-linear data structure. As we already know that data structures are just data, but they have different structures which gives them a different type of advantage. So in case of binary trees, if we try to perform a search operation or even some other operations, it can give us a very less time complexity, which we will see in a later bit. So let's try to understand how the data structure looks like. What is the arrangement of data? So let's consider we have this data first. And here, now let's say we want to insert this data inside of the binary tree. Every binary tree starts from the very first node, which is also known as the root node. So the first task in writing the program to create a binary tree is to assign a root reference, which initially will be pointing to a null value. And then when we want to insert a value inside of the binary tree, we are going to make this reference to point to this node. Every node inside of a binary tree is going to have a same fundamental unit structure, which is we will have a node with some data and we will have two different directions or two different memory references. The first one will be the left memory reference and the second one will be the right memory reference. Initially, when we are trying to create a fundamental node, this node is going to look something like this, and these references are going to point to the null values. Now, when we want to construct a binary tree, we are just going to push this node inside of the binary tree. So let's say we want to push 5 inside of the binary tree. We are first going to create this fundamental node, and we already know that we can create an object of this class node, which will construct this object and it will allocate this data and these two references in the memory. So 5 will be allocated with two references which are initially assigned as null. And we are going to make sure that the root is now pointing to the 5, which is the first node, instead of null. Now let's say we want to insert some more data, 4 and 6. So here, let's say I want to insert 4 and here I want to insert 6. And we know that when we want to insert any node, every node will have two different pointers and they are going to point to null. So we will have to make sure that the left memory reference will be referencing to the element that we wish to insert in the left part of the tree. So let's say I want to insert 9 in the left part of this. So I will have to make sure that first I allocate it by creating an object of the node class and providing the data by at the time of object call. I can just provide the data. Let's say I want to create a node 9. I can just provide the data 9 and I will create a constructor to construct this object. Whenever we create an object, we know that it is actually stored inside the main memory. So whenever we create any object of this node class, which we will see when we will program it in Python, it is stored inside the memory. Now after calling 9, we will have an object which has data as 9 and two null references. Now let's say we want to insert 10, 15 and 13. So let's say I will insert 10 here, I'll insert 15 here, and let's say I will insert 13 here. All the nodes we know will have two pointers, which are pointing to null. Now, since we do not have more data to insert in this binary tree data structure, all of these are going to be the null references. So here I am just using a null symbol to represent that these are null references. Now let's understand one important concept, which is what is leaf nodes. So here you can see a leaf node is a node which has the left and the right references as null. So 15 is a leaf node inside of this structure. And similarly 10 and 13 are also the leaf nodes because they also have left and right pointers pointing to the null values. So all of these data which is 13 and 10, they all are leaf nodes. Now let's come to the very important part, which is the height and depth of the tree. The height and depth of the tree is very important because it will help us evaluate the time complexity of different operations in a binary tree. So let's suppose, let's first come to the topic, which is the height of the tree. Height is calculated as the number of edges that goes from the root node to the node with the longest path. To the node with the longest path. So here we can see that the longest path is from 5 to 4, then 9 and then 13. So from root to 13 we will calculate the number of edges, which is 1 from here to here, and then 2 and then 3. So there are 3 edges from root node to the longest path. So the height of this binary tree is equal to 3. Now let's come to another term which is also known as level of a binary tree. Level starts from 0. So at level 0 we have node 5. At level 1 we have nodes 4 and 6. At level 2 we have nodes 9, 10 and 15, and level 3 has 13. So this is going to be the level 3. As we can see here, if we want to find out the number of nodes inside a level, we can just do 2 raised to the power the level, which is 2 raised to the power L. So here 2 raised to the power 0 will give us 1. 2 raised to the power 1 will be equal to 2. So there are 2 nodes. Height of this binary tree is 3. Now let's consider what is a subtree. A subtree is a part of a tree which actually is not the whole part, but it is just a smaller section of the tree. So here we can assume that this is one of the subtrees of this binary tree data structure. We can also consider this one as a whole subtree. We can even consider a single node as a subtree. So these are the possible subtrees inside of this binary tree data structure. Now let's see how we can calculate the height of a particular subtree. So let's say I want to calculate the height of this subtree, which is 4, 9, 10 and 13. So we want to find out the height of this subtree. We will apply the same concept that we were applying to the height of the whole binary tree. We will consider this as a whole binary tree. So we will start from the root of this subtree, which is 4, and then we will move to the longest path, which is 13. So the height of this tree will be equal to 2. Now let's move on to another important term, which is known as the depth of the binary tree. Depth of the binary tree is defined as the number of edges from the root node to the node that we wish to calculate the depth of. Now let's say I want to calculate the depth of 6, or let's say here I want to calculate what is the depth of 4. So from the root node to 4, we have only one edge. So the depth of this node 4 is going to be the value 1, which is the number of edges from root node to the node which we wish to calculate the depth for. There is a huge confusion between the height and the depth of a tree, so I will like to clear that. Height of the tree is actually number of edges from the root node to the last node of the longest path, whereas the depth is the actual number of edges from the root node of the tree to that node. So that's how we can calculate the depth of the tree and the height of the tree. Now let's take a look at how this tree is going to be stored inside of the memory. As we all know that all the data is going to get stored inside the memory. So the first thing is I'm going to draw a structure of memory here. And we know that memory is divided into several continuous blocks which can store some data. Let's say each of these can store 1 byte of data. We know that the memory it has memory locations which are continuous in nature. So for example, I'm just assuming that this memory starts from 1001 and goes 1002, 1003 and so on. Now we can see here that binary tree is actually having 2 branches, but it is not the way it is stored inside the memory. It is going to get stored inside the memory in a different fashion. So let's say we first create an object of the node class by allocating 5, which will allocate 5 in the main memory, and it will have 2 pointers, which is left and right, which is initially pointing to a null reference. Now let's say we wish to enter 4 inside of the binary tree. So let's say 4 is allocated here. Now programmers do not have control over where you can store a particular element inside of the memory because it is unknown where the memory block is empty. So here let's assume that 4 will be inserted at this memory location, which is 1003. Now we know we have a left pointer. So what we are going to do is this left pointer will get assigned to this memory location. So this left pointer will hold the value of 1003 to tell that this is going to be the left part of the tree. Now the right part is 6. So let's say 6 is stored here. So similarly, we are going to create another pointer which is right, and right is going to have the value of 1002. We are just assuming these values. These are not the absolute values. We are just assuming them just for the sake of explaining how a binary data structure is stored inside the memory. The memory is a linear data structure, but we can use references to actually get this hierarchical structure. Now let's come on to the very important topic, which is different types of binary trees. The first type of binary tree is known as the degenerate or the pathological tree. A degenerate or a pathological tree is a tree which actually can be used as a linked list. So let's insert these same elements inside of a degenerate tree. So we have the first element here 5, then we will insert 4, and the right part is being null. Right part of every node will be equal to null, and we can only insert it in the left part. So after 4, 6 will be inserted here, and then 9 will be inserted here, and then similarly 10, 15 and so on. We can also do the opposite, which means that we can also insert the elements on the right part. In that case, the left references are going to be null. Now you can see the height of this particular type of tree is going to give a time complexity of big O of n, because you can see that it is actually a visualization of a linked list as a binary tree. Next binary tree, which is a very important binary tree, and it has a lot of applications in data structure is known as a balanced binary tree. A balanced binary tree has a difference of the height of left and right subtree at most 1. This restriction makes a binary tree as a balanced binary tree. So whenever we are given a binary tree, we try to make sure that it is a balanced binary tree because it will give us a time complexity of big O of log base 2n. And the reason for this is that a balanced binary tree has a height equal to log base 2n. That's why the time complexity will be equal to log base 2n. So now let's see how a balanced binary tree looks like. In this example, let's see whether this is a binary tree or not. So this is a binary tree. Let's see whether it is balanced or not. So here you can see I have this node here. The height of the left part of the subtree is equals to 2. So height of this tree is equals to 2. Let's consider the right part. The right part has a height which we can see here. From here to here we have the height is equals to 1. So height of this will be equal to 1. So the result is actually equal to 2 minus 1, which is equals to 1. The difference should be at most 1, which means that it cannot exceed 1. Here we can see that it is not exceeding 1. So this is a balanced binary tree. Such type of a tree can give us a time complexity of log base 2n. This application is actually very useful because in case of degenerate or linked list, we are having a time complexity of big O of n, which is greater than the time complexity of log base 2n. So we prefer a balanced binary tree. There are certain variations of a balanced binary tree which we will study in the further tutorials, which is the red-black trees, then the AVL trees. So we will study them in detail in the upcoming tutorials of this course. Now let's understand the third and the very important part, which is a perfect binary tree. A perfect binary tree has 0 or 2 children in all the nodes. An example of a perfect binary tree will be something like this. This is an example of a perfect binary tree. This is also an example of a perfect binary tree. I can extend this more, right? We can have 2 or 0 children. It is also a perfect binary tree. This one is also a perfect binary tree, and so on. Now let's perform the implementation of binary tree. In the next tutorial, we will first create a class node, and what we will do is we will create a binary tree with the root reference initially pointing to null, and then we will keep on inserting these nodes to form a binary tree. Before moving on to that, we first need to understand a very good variation of binary tree, which is known as a binary search tree. Binary search tree is optimized for searching operation. So if we want to search a particular element, we are going to make sure that the left part of the tree will have the value of the node should be greater than or equal to the root node, or we can say the parent node. And for the right part, the value of the node will be less than or equal to the root or the parent node. We can even do the opposite of this to obtain a binary search tree. Binary search tree with these restrictions makes the search operation optimized. Let's see how. Let's see how we can insert this data inside of a binary search tree. So first we will insert 5 as the root element. So here I will insert 5. Then we have 4 here. 4 is having a value lesser than 5, and we say that if the value of node is less than the parent, it is going to go to the right side of the tree. So 4 will go to the right part. Then we have 6. 6 is greater than 5, so 6 will be inserted here. Then let's consider the next element, which is 9. 9 is greater than 5 and is also greater than 6. So if it is greater than 6, we know that it is going to come to the left part of the tree. Then we have 10. Now 10 is greater than 9. So again it is going to come to the left part of this tree. Now 15 is also going to the left part. So that's how we are going to insert the elements in the binary search tree. So in the next tutorial, when we will try to insert the nodes, we are going to form this type, we are going to use these restrictions to insert the node in the binary tree. And this will actually is an optimized search, because you can see here, if I want to search 9, first I will go to the root node. I can evaluate whether 9 is lesser than 5 or not. If it is greater than 5, I know that I do not need to traverse to all these elements which will be there inside of this tree. We will do that again and again recursively, ignoring the branches that we do not need to find or traverse through, which makes this optimized search. So in the next tutorial, we will start with the implementation part of the binary tree. So that's all for this tutorial. Thanks for watching.